Hello. Good evening, and welcome to the third episode of Shocking Hour. I'm so glad you decided to join, and I'm super excited to have you guys join today's live stream. Now, yesterday, if you were able to join, we did talk about dimensional equations yesterday, and we looked at some how to write the dimensional equations of some quantities or parameters like force, area, moment, and many others. Now, today we are going to continue with dimensional equations, but we are going to look at the third uses of dimensional equations. Now, yesterday, if you remember, when we were dealing with dimensional equations, I did say that dimensional equations have three uses. The first use we said, um, let me quickly write that down, just a little recap of what we did yesterday. So a little recap. Yesterday, we established the fact that dimensional equations, we can use them to find the units of quantities, the units of quantities. So, for example, over here, we established that for acceleration, we said for acceleration, if we find a dimension for acceleration, which is velocity over time, the dimension for velocity on time, we established the fact that just velocity alone is lt minus 1, all over time is t, and so therefore the dimension for acceleration is lt minus 2. Now that we have this, from this we can derive the unit. Mind you, let me use a different color. Mind you, L is for length and T is for time. And we know very well that our length or length is measured in meters, and then time is measured in seconds. So we have meters per second square over here as our unit. And this was derived from this as the dimension for acceleration. So this is what we established yesterday. We can use dimensional equations to find the units of quantities. All right, let's proceed. So for the second one, we said we can use it to check the validity the validity of an equation. We also use dimensional equations to check the validity of an equation. Okay, now in using it to check the validity of an equation, yesterday we looked at some examples where we were able to establish how we use dimensional equations to check the validity of an equation. Now today we'll be looking at the third uses of dimensional equations, and that is to derive equation between quantities. So how to derive an equation, between quantities, and this is what today's live stream is all about. It is us using dimensional equations to derive um, equations between quantities. All right, so let's look at an example so that you will be able to appreciate what we are doing. So we have here a problem that we are supposed to solve using our understanding of dimensional equations that we did during yesterday's live stream. So we have here the period of oscillation of a single pendulum depends on mass m, length L of a thread, and acceleration due to gravity g. Using dimensional analysis, we are to derive a formula for the period of oscillation. So this is the problem that we have, and this is the problem that we are supposed to solve using dimensional equations. Now this is very, very easy. So grab your pen and paper and let's look at how to solve this particular problem. All right, so the first thing I'll do here is to write down my solution, and then I read the question again. So they said the period of an oscillate, the period of oscillation of a single pendulum depends on the mass. So the period, I'll represent the period with T. They say it depends on mass. So it depends on mass, which is m, length L, and then acceleration due to gravity. We have to use dimensional analysis to derive the formula for this period of oscillation. Now, what I do over here is that they say the period depends. We don't know whether it depends directly or indirectly. So we write T and then we bring this sign. It means it is proportional. Whether directly or indirectly, we don't know. So it is proportional to M, which is the mass, L, which is the length, and then gravity, which is our G over here. Now from here, what we do is that we remove the proportionality sign, and once we remove that, we introduce a constant k. So we have here our period is equal to the constant. Let me use a different color for the constant. So we know that that doesn't affect anything. So we have the constant k, and then we have the m, the L, and then the G over here. So what we'll do over here is that we will introduce some powers for this particular quantities. So here for the m we give it x, for the L we give it y, and then for the G we give it power z. Now you can use A, B, C or any alphabet to denote it, but x, y, z, it makes it much easier. Now from here, what we do is that we now find the dimension for the period, which is equal to, like I said, the constant is the constant, so we don't do anything for it, we just leave it there. And then we find the dimension for the mass, then the power is outside it, then we find the dimension of length, then multiplied by raised to the power y, then we find the dimension of gravity raised to the power z. Okay, so this is what we are going to do, and then we proceed. Now the period of oscillation, period is the same as time and it's measured in seconds. Are you okay? So the dimension for time, as we saw yesterday, is t. Okay, so the dimension over here for this is t. So let me use a different color so that we appreciate that. So the dimension of time over here is t. Then this is equal to the constant. For mass, the dimension of mass is still m. So I write my capital M. Then I bring the power x. Then I have over here length. The dimension of length is still L. So I bring the L raised to the power y. Now for acceleration due to gravity, in dimensional analysis is treated also as acceleration. Now we know that the dimension for acceleration in this case due to gravity will be the same as over time. And when we find the dimension for this, yesterday we established the fact that for velocity, the dimension is lt minus 1, and then the time at the bottom here is t. So the dimension for acceleration, which is the same as acceleration due to gravity in this case, will be lt raised to the power minus 2. So this becomes the dimension for acceleration due to gravity over here. So in this case, what I will write over here is into bracket. For the gravity, we have this as our dimension. So I have lt minus 2. Then I bring the power z attached. So far, this is what we have. So from here, I've already expressed the quantities I've been given into their respective dimensions. And now that I have expanded them, or have expanded them into their various dimensions, what I need to do is to simplify. So from here, what I will have is, so let me separate this from the top. What I will have here is, I'll have my t is equal to my k. The m will still have the power x. The l will still have the power y. But over here, I have to multiply through. So let me remove this bracket first. So my L over here, the Z to multiply the L, okay, the powers. So I'll have here L raised to the power Z. And then for the T over here, to be T raised to the power negative 2Z. So I'll have here T raised to the power negative 2Z. So this is what I have. Now from here, I can see that L power Y and then L power Z, they are multiplying each other. Remember, everything here is multiplying each other. But in indices, when we have the base being the same and they have powers, all you do is that you add the powers. So over here, I have my time to be equal to, or my t, the dimension for period, to be equal to k m raised to the power x. The L over here, the power y plus z, and then t raised to the power minus 2z. Are we okay? So this is the expression that we have so far. And if you don't understand, let me know in the live chat so that I go over again. But so far, if you've understood all we've done up to this point, kudos, and then we can now proceed to solve this problem. Now from here, all we have to do now is to find their respective powers. So what we do over here is that we look at our left and our right hand side, and then we compare powers. Okay, we look at the left and then we look at the right, and then we compare powers. So over here, we see that on the left hand side we have t, and then on the right hand side we also have t. So we'll compare t first. That is the first thing we will do. So in comparing t, I have over here, so I will say comparing powers of t. Okay, now when I'm comparing the powers of t, I have here t, it is raised to the power 1. So just the powers, I'll write 1 over here. That is equal to, if I compare to the t over here, this is raised to the power negative 2z. So this is minus 2z over here. Are you okay? Now from here, the next thing I will do is that I have to find z. So I divide both sides by negative 2. This cancels this. So therefore, z is equal to negative half. Okay, so this is what I have for z. Are we okay? Now, after finding z, I need to proceed to compare the powers of L, the next thing I have over here, to find my answer. So let me rewrite the expression I have over here and then we continue. So what I have is, I have t is equal to k m to the power x l power y plus z, and then t raised to the power minus 2z. And we've already found that z is equal to negative 1 over 2, which was what we found over here. So now we can proceed. This one is not needed. You don't need to write it over here, but I'm just continuing. So we'll just continue by comparing powers of L. Okay, now we are comparing the powers of L. Now to compare the powers of L, on the left hand side we don't have any L over there, so the power over there is 0, and this is equal to, on the right hand side we have y plus z. Are we okay? Now we already know the value of z, which in this case will be equal to, the z is negative half, so I have minus 1 over 2 over here. So if I make y the subject and I send the half over here, I have half positive is equal to y. So therefore, my value of y is equal to positive half. Now I can now proceed to compare powers of m so that I find the value of x. So over here, I'll continue by saying comparing powers of m. Are we okay? Then again, I ask myself, on the left hand side and then on the right hand side, do I have m at both sides? In this case, it's no. So it means on the left hand side, which is this side of the equation, I have no m, so it is 0. The power is 0, and it's equal to, on the right hand side, it is x. So therefore, it means the value of x is equal to 0. So if you look at all we've done so far, we found out that x, the power is 0. For y, it is half. And then for z, it is negative half. Are we okay? Now, just quickly, let me go back to the previous equation. Now, remember, this is our initial equation given to us, which is the period is equal to the constant, the mass, length, and gravity. So now that we found x, y, and z, we will go back to this equation and then insert those values there to find the relationship between these parameters. So over here, I will write that expression, the expression that I just showed over here, this expression. I'll rewrite it over here. So I have t is equal to k. Then I have m raised to the power x, l to the length, m is the length. So I have that to the power y, and then gravity, which is g to the power z over here. So over here, I have my period given to me. So I have t is equal to my k over here, and then m raised to the power 0, l raised to the power y, which is half, and then g raised to the power negative half. So from here, all we have to do is to rewrite everything we have over here in a more simpler form of writing mathematical expressions. All right, so what we have over here is now going to be written like this. We have t is equal to, for my k is still here, m raised to the power 0 is 1, so it is out. Then l raised to the power half is root l. And then for g raised to the power negative half is the root of 1 over g. Are we okay? Now this can be rewritten as k. Then because the root is here, we can rewrite everything as l over g. Okay, root l multiplied by root 1 over g will give us this over here. So this is the relationship between the tension, the period, the length, the mass, and acceleration due to gravity. So what it tells me is that my period of oscillation over here is from this expression. You can see that the T is here and then the L is here. So the period is directly proportional to the root of L. Okay, it is directly proportional to the root of L, or L raised to the power half. And then at the same time, the period is inversely proportional to the root of g, 1 over g. Are we okay? Or basically, the period is directly proportional to length, and then the period is inversely proportional to acceleration due to gravity. And this is the way they are related. For the L, it is directly proportional to the root of it, and then it is inversely proportional to 1 over g for gravity. Okay, so this is how we find the relationship between expressions using dimensional equations. Now, I know this is a lot to take in. If you are doing this for the first time, this might be a little bit overwhelming for you, but this is the expression, this is our answer. Okay, so if you have any question, you can ask in the live chat. If not, we will continue to see another question. So I'm just going to give us some few minutes, say 1 minute. Let's ask questions and then we can proceed. Any question? We can drop our questions in the live chat. Any questions so far? Okay, so I'm looking through the chat to see if we have any question. Okay, so we don't have any question, so I will proceed to continue with the next example. Now, if you don't understand and you want to listen to the explanation all over again, you can go back and watch the live stream after we are done. All right, so this is the second example that we have, and I really appreciate if we can try it ourselves before I look at it. Okay, but all the same, this is the second question. So we have the frequency f of a vibrating string depends on the length L of the string, the tension T in the string, and the mass per unit length U of the string. We are to derive an equation between the frequency, the length, the tension, and the mass per unit length, which is mu, for this particular question. So this is the question that we have. Now, this is also simple. We just look at it like what we did in the previous example, and we don't have any problem. All right, so let's dive in and look at the solution to this particular problem. All right, so I'll write down my solution. Okay, very good. Now, we were told that the frequency f of a vibrating string depends on, so we have our frequency f depends on the length, so I'll write L of the string, the tension T, right, T here of in the string, and the mass per unit length mu, so mass per unit length of the string. Okay, so this is the expression that I have. Are we okay? Now, to remove my proportionality sign, I will then introduce a constant. So my frequency is equal to a constant K, and then followed by the length, the tension, and then mu. Now, mind you, F is frequency. There's a reason why I'm writing this. L is length. T is tension. And then this is given to us as mass per unit length. Okay, this is what we've been given. So now all I have to do over here before I proceed to do any other thing is to give these quantities some exponents or powers. So I'll give the L x, I'll give the T y, then I give mass per unit length z. So from here I find the dimension for frequency is equal to k, and the dimension of length is the power x, then the dimension of tension raised to the power y, then the dimension of mass per unit length to the power z. Now let's go back to frequency. Now frequency is inversely proportional to time or period, so it is 1 over t. Now we know that time or t, the dimensional equation for t is still t. So in this case 1 over t will be rewritten as t inverse, or t raised to the power -1. Now for L, which is length, the dimensional equation for length L is still L. So it's still just capital L. Now for the T here, which is tension, let me do that here. For the tension, tension is a type of force. Are we okay? So in this case, we'll use tension also as force. And what is force? Force is mass times acceleration. Are we okay? And the dimension of mass is m, and then the dimension of acceleration, we've looked at it severally, is lt minus 2. So therefore the dimensional equation for tension is mlt minus 2. This is the dimensional equation for tension. Now for the next one, which is mu, which the definition is telling us mass per unit length. Mass per unit length means mass over length. Are we okay? And for mass, the dimensional equation for mass is m. The dimensional equation for L, which is length, is L. So I have here ml -1. So this is this. So if we look at it so far, the dimensional equation for frequency is t raised to the power -1. For length is just L. For tension, it is mlt raised to the power -2. Then for mass per unit length, or mu, it is ml raised to the power -1. So now that I have these parameters, all I have to do is to go ahead and substitute them into this expression. So I have over here my frequency, which now becomes T inverse. So I have here my frequency. So my frequency, in place of the frequency over here, I'll write T inverse. So I have here T raised to the power -1 is equal to I have my constant K, and then I have here L. Now in place of L, I'm going to write capital L because it's still the same. So I have L raised to the power X. Now for the tension, in place of tension, I open bracket here. Tension, we said, is mlt raised to the power -2. So I have here mlt raised to the power -2. And then I put y at the top. And then for mass per unit length, or mu, I have here into bracket ml raised to the power -1. Then I put z at the top over here. Are we okay? So this is the expansion that we have over here. So all I have to do is to further expand everything I have here, and then I go ahead to compare their powers. All right, so in the meantime, this is what I'll do. Let me quickly get rid of this side works, and then we proceed with the main work. Okay, so from here, this is what is the power x. Now I'll use the y to multiply through everything I have over here. So I'll have m raised to the power y, L raised to the power y, and then t raised to the power -2y for this side. And then for this side, I will have m raised to the power z, because I'm using the z to multiply through, and then l raised to the power negative z. Are we okay? This is what I have. Now, mind you, I have quite a couple of things over here. For L, I have 1, 2, and 3. And this is, once they are the same base, we add the exponents. And then for M, I have M here and then M here. I also have to do some grouping over there. So this is what I will have next. I have T inverse is equal to K. The L is 3, so I have L here. Will bring the negative Z over here, okay, because all three values are over here. The next one I will do is that I will now compare the powers of L to find my next answer. So to do that, I'll use red. So I'll compare. So over here, I will maintain the 0. My x is still unknown, but my y is positive half. Then the negative here is here, and then the z itself is negative half.